Okay, we're going to go ahead and finish up section 1.4. At our last class meeting, we talked about the limit definition of the derivative. So as you recall, the derivative is denoted by f prime of x, and we define the derivative in terms of limits, as you see here. The limit as h approaches 0 of the difference quotient. Okay, so we looked at the difference quotient before. And so if we evaluate that and take the limit as h approaches 0, we will then find the derivative f prime of x. Okay, the steps that we learned about at our last class meeting were as follows. So first of all, we want to write the difference quotient. Then we want to simplify the difference quotient. And then we're going to take the limit by letting h go to 0. And then the quantity that we get will be the derivative, f prime of a. So we worked this example in class already, and now we're going to build on that and work another example. So we're asked here to find the derivative of 1 over x, where x is not equal to 0. And so to do that, we're going to first of all write our difference quotient and take the limit as h approaches 0 after that. So what we're doing, we're taking the limit as h approaches 0 of 1 all over x plus h minus 1 all over x all over h. Okay, remember this quantity here, that is our difference quotient. Okay, we simplify that difference quotient before we take the limit, and so in the numerator we need to get a common denominator. So in doing that here, we multiply by x over x, by x plus h all over x plus h. All right, and then what we get as a result would be then x minus, we need to distribute that minus 1, minus x minus h all over x times x plus h all over h. Okay, we'll continue now simplifying that difference quotient. And so we see here that the x's subtract out, which is very nice. And so we're left with just negative h in the numerator. So I'm going to go ahead and write this down just a little bit clearer. So what we're doing here, we're taking the limit as h approaches 0 of negative h all over x times x plus h. And I'm going to write that as times 1 all over h just to eliminate that complex fraction. Okay, and then dividing, our h's go out, leaving us with just negative 1 times 1. So we have here negative 1 all over x times x plus h. Okay, and now we're going to take that limit as h approaches 0. So we're going to let h go to 0. And so when we do that, what we'll have is negative 1 all over x times x plus 0, which is negative 1 all over x squared, and that's the derivative. Okay, so f prime of x equals negative 1 all over x squared. So this right here is our final answer. Okay, and so continuing on for our next example, we're going to find the derivative of the square root function. So we're going to take the limit as h approaches 0 of our difference quotient. And so we write the square root of x plus h minus the square root of x all over h. And there's a little trick here that we do. We multiply by the conjugate. Okay, so whenever you have radicals in your problem, you always want to use conjugates. So take the conjugate of the numerator, which would be the square root of x plus h plus the square root of x, okay, all over the square root of x plus h plus the square root of x. So again, when you have radicals, this is the technique you're going to use. You're going to use conjugates. Okay, and so now we simply distribute across the numerator, and so We have some of these radicals going away, which is really the purpose of multiplying by those conjugates. So we have the limit as h approaches 0, and then we have x plus h. Notice that the outer and inner terms subtract out. So this outer and inner terms subtract out, and then finally multiplying those last terms, we have negative x all over h times the square root of x plus h plus the square root of x. Okay, and so now we're going to continue simplifying, noticing here that our x's subtract out, okay, our h's divide out, leaving us with just 1, and now we're all set to let h go to 0. So letting this h here go to 0, I have 1 all over the square root of x plus the square root of x, which is 1 all over 2 times the square root of x, which is our derivative. So that's our final answer. Okay, moving along. Now we're going to talk about the idea of infinity, okay, and how to deal with limits. So far, we have dealt with the limits as x approached some constant, okay, like maybe the limit as x approaches 3 for some function f of x. That's what we've encountered up to this point. Now we want to consider what happens when we take the limit as x approaches infinity. In other words, if we let x get infinitely larger, what happens to f of x, okay? So if we look at figure 2, this is just an example to look at. We want to take a look at what happens when we let x get bigger and bigger and bigger. So we want to find out what happens as x approaches infinity. And as we trace our curve here, we can see that our curve, as we let x get closer and closer and closer, we're approaching 2. So the limit as x approaches infinity here for this particular example is 2, okay? For this other example here in figure 3, we're going to take a look at what happens when x approaches negative infinity. So we're going to take the limit as x approaches negative infinity and take a look graphically at what's happening. So we have a function here, f of x. Instead of going in the positive direction, we're letting x go to negative infinity. We look at our curve, and our curve is getting infinitely closer to the x-axis. So the limit as x approaches negative infinity is 0. Okay, and then we'll do one more example. We want to calculate the following limit. The limit as x approaches infinity of 8x plus 10 all over 4x minus 3. Okay, there's a little trick here to employ as well. You want to divide the numerator and denominator by x. Okay, and so that will give us a quantity that we can then evaluate. So we're going to take the limit as x approaches infinity of 8x all over x plus 10 all over x all over 4x over x minus 3 all over x. So divide each and every term in the numerator and denominator by x, okay? And we're going to see the utility of that in just a moment. Let's clean it up a little bit. We notice that these x's divide out, right? So we're left with just 8. Then we have 10 all over x. In the denominator, our x's divide out, so we're left with 4 minus 3 all over x. All right, now we want to take the limit as x approaches infinity. In other words, these x values are getting bigger and bigger and bigger. Now, as you let the denominator of a fraction get bigger and bigger, and the numerator is a fixed constant, then that entire quantity is going to go to 0. To make sense of that, you can think of the function 1 all over x, right? So here's the graph of 1 all over x. You notice as x gets bigger and bigger and bigger, then your function, f of x, right here, is getting closer to the x-axis, so it approaches 0. So this right here is going to go to 0. this is going to go to 0. And so we have 8 all over 4 left, which is 2. So that's the final answer to the question. So the limit as x approaches infinity of that rational function is just 2. Okay, so on Wednesday, we are going to start out with section 1.5, which deals with differentiability and continuity.